This is section 6.5. And in this section, we will try to applying integration to calculate the amount of work done in performing a certain physical task. That means we will just focus on calculating the work, applying the integration. So in general, work is, we using the term work in like everyday language, and it means the total amount of effort required to perform a physical task. But like to be more like using the technical meaning, we can say that the work is the force that we can apply to an object to move it, yes, to this place. That means in general, we probably remember the formula for the work is just force times the distance. Okay, and everything is perfect and easy if the force is constant. Yes, if the force is like all the time the same on the entire interval. If it's not the same, if it's changing, we have to look at that change, evaluate the change, estimate the change, and add together all of the forces on that interval. Then we will have a correct work computed. Okay, and this is some information about the work. I mean, let's talk maybe about the force for a second. That means force based on the Newton's second law, we know that is mass times the acceleration, and acceleration is the second derivative. I can use this notation, and units. Yeah. In SI metric system, mass is in kilograms. A second derivative, we know that is the rate of change of the distance with respect to time. That's the first derivative. And then again, with respect to time, then we have distance, like meters over the time squared. Time is in seconds. Times the mass in kilograms. And we did create a new unit, which is called newtons. Newtons that's the unit for force. It's worth to know it. Kilograms times mass over second squared. Or we can say, and yes, and 1 Newton is basically force acting on, like, I mean 1 Newton force is 1 Newton is the force acting on 1 kilogram, produce an acceleration on 1 meters per second squared. Okay, so simple. Okay, and then we can also say force is the mass times g, and g is the acceleration due to the gravity, 9.8 meters per second squared. And that's how we can always multiply mass by the acceleration due to the gravity if we're using a metric system, SI metric system. Because now let's look at the other system, which is called imperial system, or British system, or US customary system. Yeah, we will have weight, and actually weight is force right away. Weight is not a mass, which we can say kind of like weight includes the acceleration due to the gravity. That's when in imperial system, the factor g, the acceleration due to the gravity, will not appear. Yeah, we will just basically computing a force. We will know the weight is actually the force. Okay, unit of force, and the units will be pounds. Okay, that's the SI metric system. Yeah, a little bit of physics introduction. Okay, and now we just know that the work, the formula is force times the distance if the force is constant. But we will focus today on the force that is not constant, that the work that we have to produce, like required, will not be constant. Okay, what other information we have? Yes, force is measured in newtons, we know that. Newtonometer, yes, that means work. If force is in newtons, then Newton times the meter, we will have newtonometer, which actually is called joule. That means work, the unit for work are joules. And if we have the imperial system, it will be, the force will be measured in pounds, and the distance in feet, we will have foot pound. And this is like 1 foot pound is equivalent to 1.36 joule, if we would like to get some connection between the SI metric system and the integral system. Okay, in general, but this is important. This formula is important. Formula for the work is equal to force times the distance. It is constant force. Okay, so now let's look at the really easy question. Example number 1. How much work is done in lifting 1.2 kilograms book off the floor to put it on the desk that is 0.7 meters high? Use the fact the acceleration due to the gravity is 9.8 meters per second square. Okay, as we know that work is defined as a force times distance. Force, because that's the metrics, it's mass times the g, the acceleration due to the gravity, and distance that we will apply the work for is 0.7. Okay, mass is 1.2, 9.8 meters per second square, and the distance 0.7. Just multiply everything, and the units will be Newton or meters. However, that's the joules, 8.2. You can check the arithmetic. And now, part B is in the imperial system. How much work is done in lifting 20 pounds weight? 20 pounds weight, 6 feet off the ground. Okay, so now we don't need anything. We just need to multiply force, because the force is basically the weight. The force is the weight if the units are pounds. 20 times 6, that means force, the weight over the distance, 6 feet, 100 feet pounds. Okay, that's simple. You may pause the video, you may look at this solution, but now let's try slowly answer this question. We know that work is defined as a force times the distance if the force is constant. However, what happens if the force is a variable, if the force is changing of any interval? This is the interval AB, and let's say the force that we applying is not the same. Moving this is not the same. We're getting tired, or other parameters other condition will play a role. That's what we will do. We will apply the integrals. We will try to focus on tiny interval. Yeah, let's pick this one. We will call delta x, we dividing by subintervals. They are extremely tiny. You probably know that delta x is approaching almost 0. And on that tiny interval, we will assume that the force is constant. Yes, we will assume that the force is constant. That means the work done on that one subinterval will be force, and times the distance. Distance is delta x. And then we can add all of them. That means that we can assume that the work is constant. Force is constant on every single interval. That means adding all of them. Yes, delta x from 1 to n, right? Then we will have the work done for all of them. And now, if we would like to have, this is still kind of approximation, yes? But when we take infinitely many of these sub-intervals, let's say this, n goes to the infinity, then we know that adding all of this tiny work, the force times the distance for every single subinterval, adding infinitely many of them, that's the integration. Limit of the sum is the integration. This work is happening from A to B, and we just have to, and let's say will depends on x. The force will depend on x, and delta x becomes dx because we will integrate from A to B with respect to x. That's actually, that's basically what we have to do. We have to just integrate force if we know the formula for the force. Let's see. Let's still add a couple of things, but that's what we will do. In order to get the work, we will integrate force. Okay, and I have the really detailed description, dividing, and I think I type it, let's see. Yeah. This is for, okay. Yeah, I think that means this is work for one like sub-interval, assuming that it's constant. This is adding all of them. And then for the good approximation, we're adding infinity many of them. That means now we just have to integrate, right? Let's see this. The work performed in moving an object along the x-axis from A to B by applying a force f of x is just the integral from A to B f of x dx. Yeah, let me come back for a second. Yes, we did have the same. We remember these steps from section 6.1, 6.2 for the area and for the volume. We always applying the same thing. We adding, slicing and adding. That's integration. Depends. Area, volume, force, work. Okay. Now that's the formula, but we still have to be careful because we still will have some questions involving a mass, maybe some volume, maybe total mass, include like the density and all of these additional parameters. Okay, let's solve another example. When a particle is located at distance x feet from the origin, a force of x squared plus 2x pounds act on it. How much work is done in moving it from 1 to 3? So we know that function is definitely changing from 1 to 3. In order to compute the work, we will just, I can maybe say this, from 1 to 3, we will just, this is force, integrate force. Because we know that this is taking care of every single like moment from 1 to 3. Then the changes in force is like calculated. Okay, so simple. We know how to integrate this. That's the integral, that's the evaluation. And then we have 16 2/3 feet pounds. Okay, but that's the imperial units. Let's look at the next example. Okay, example number 3. 200 pounds cable is 100 feet long, okay, and hangs vertically from the top of the building. How much work is required to lift the cable to the top of the building? That's we can imagine we are here and we have to lift the cable, like pull to the top. Definitely, if it's longer, we required more work, and it requires more work. If it's shorter, it requires less work. That means definitely the integration will take care of this exercise because we cannot. Definitely the force is not constant. Okay, that's what I will do. The cable weighs 2 pounds per foot. 2 pounds per foot, then we can say 2 pounds per, yes, I mean, it's 2 pounds per foot, but how I did calculate this, because was 200 pounds per 100 feet, then it's 2, when we simplify, it's 2 pounds per foot. Okay, that's actually the force, that's the weight is the force. That means the weight is the force, and I can say 2, and the thickness, yes, the distance that we're moving is delta x. Yeah, this is the delta x. Okay, that means that small part, maybe let's say this way, this small part, this delta x, this will weight 2 times this length, yeah, the tiny length. That's the way to say. The weight of this small, the weight of this small part, the I part, is 2 times that part, 2x, because it's 2 per foot. That means 2 per this, 2 delta x. Now, the work done by this small part, this red part, yes, will be force times the distance. Right? And that's what I was saying. Force is just the weight. That means that force will be 2 delta x. Yeah, but it's 2 pounds times that small length. 2 times delta x, and the distance now, the whole distance is, we can see it's this x sub I. Because this small subinterval, this small part of the cable is at the level x sub I. When we pull out, it will be, x sub I will be higher and higher and higher. That means this will change from 1, yes, from 0 to 100 or from 100 to 0, but it will change. And I think that's the reason that we have sample point x sub I. Okay, it means now I just changed the order to x sub I delta x, because delta x is not changing, it's approaching 0. And then this is work done by the small part, one part of the cable. This will be the total, because we will be adding all of these delta x's. Yeah, all of these delta x's. I will add all of them, and we want them to be infinitely small, then the approximation is good. Then limit of the sum is just the integral. Integral means that we adding that, yes, that work on the every single subinterval. Oh, this is supposed to be, oh, okay, we can have it this, or we can also have it limit of the Riemann sum. Okay, 2x sub I delta x, because delta x will become dx, is changing from 0 to 100. That's the length of the cable. Okay, that's we can see. We just have to integrate that work. Yes, 2x delta x, 2x dx. And when we integrating, it will be 10,000 feet-pounds. Okay. Let's do that. We can see this is, yeah, this is important. Okay, let's do another one. I have here solution. You can pause the video and you can read, but I think this explanation was good. Okay, example number 4. Oh, wow, my presentation. Compute the work against gravity required to build a concrete column of height 5 meters and square base of side 2 meters. Assume that the concrete has density 1,500 kilograms per cubic meters. Okay, that's because the density of the material is important. Okay, compute the work to build this concrete column. That's we will put layer by layer. It means the work performed is, of course, force times the distance, and I call the distance y. Yeah, because it's we have to put here, we have to put here, we have to put here. That's we focusing on the one, and then we will add all of them. Integration is adding. That's in, yeah, we have to put, yes, we have to apply the force to lift up to y. That's the distance. Okay, but now force of the layer is basically mass times g, acceleration due to the gravity. Now the mass of the layer depends on the density. That's we need density and amount of that layer. Density times volume, and also volume of that layer. The layer looks like a rectangular box, length times width times height. Area of the base, yeah, I can say in general for the cylinder, area of the base is 2 times 2 because it's not changing, times this thickness, which of course is delta y. We remember that, meters, cubic meters, because it's volume. Now let's put everything back to the formula of the work. Force is acceleration due to the gravity times mass, acceleration to the gravity times mass times y. Y is that whole distance. Okay, now mass is density times volume, because mass, how we can find the mass, yes, the total mass, which we know it's the volume of the object and the density. And now acceleration due to the gravity, density, volume is 2 times 2 times delta y, 4 delta y. Okay, that means that's everything. We have to just integrate this, but I will move delta y to the end because everything will stay, right? But delta y will become dy, and that's it. I have still the limit, but that's what I was saying. From that, you may skip the sigma notation, and you may just set up the integral, gravity, density, this is given, y is a variable because it's changing, yes, y will change, different force on different levels. This was part of the formula, and delta y becomes dy, okay? And from 0 to 5, because it's 5 meters high. So simple. One more time, gravity, acceleration due to the gravity, density, and the distance. Yeah, the height, and height is changing from 0 to 5. Okay. Okay, I have this, and let's substitute everything. 9.8, 1500 for y, compute the constant, and then integrating y squared over 2, substituting 5 and 0, multiplying, and then I did the math, of course. Oh, 735,000 joules, yeah? Newtonometers, we know, distance, force times the distance. Really nice question. And this, yeah, it's well organized. Let's do 2 more, and you will be an expert with computing a work. Okay, example number 5. Oh, this is my solution. I was trying to be more details, but I think this solution was clear. You can skip that slide. Okay, example number 5. Okay, let's do it. A tank has a shape of inverted circular cone with the height 10 meters and base radius 4 meters. Okay, 10 and 4. It is filled with water to a height of 8 meters. Okay, that means the blue part has the height 8. The top, the missing is 2 meters. Find the work required to empty the tank by pumping all the water to the top of the tank. Find the work, let me just check. Find the work required to empty the tank by pumping all the water to the top of the tank. We have to know the distance, what we're doing. Okay, that's me now. Oh, I have some. We will, of course, divide because the work pumping water out, yeah, depends, like if it's more water, we require more work, more force. Yeah, it's not a constant because the shape is not the same along the height. Okay, that means I will start with the same. That's what you will start. Work, to compute work, is force times the distance. And we can see we have to put up to this, right? That means that amount of water in that purple disk will be, we need the force and the distance x sub I. Yeah, that's because we have to put that water outside. And then again, that water outside. That means I will call the distance x sub I, that distance from the top to the disk. Okay, now force is mass times acceleration due to the gravity. Mass, yes, it's a water. That means we need the volume of that disk times the density. Yes, mass is the density times volume. Acceleration to the gravity, distance that we're moving up the water. Okay, volume. What is volume of that disk? Is just pi r squared times delta x, because we remember this disk is like a slab. We remember from the volumes is the area of the base, which is pi r squared. This is r. Okay, and pi r squared, and height is the thickness delta x. The problem is we have to find out what is r in terms of x, and then everything will be ready for us. Okay, everything will be ready. We have the acceleration due to the gravity. We do have density, and we will have a distance x sub I. Delta x will become dx, but just that pi r squared. Okay, what we can do, we can use, I think I have on my next slide, but we can do it. We can find out what is r in terms of x using similar triangles. We have 4 and 10. 4/10 is the same like r over that distance. Yes, because we can see we have that triangle and we have this one. This distance is 10 minus x. That means r, this one, I can use possibly different color, r over this distance. Okay, r over 10 minus x sub I, because everything is the sample. And let's solve it for r. Multiplying by cross-multiplying 4 times 10 minus x sub I over 10. 2/5, 10 minus x sub I. I mean, this is radius, of course, sample, in terms of x. 2/5 10 minus x sub I squared. Okay, now we're ready. We can just take this formula and integrate. I did substitute density of the water. I did substitute gravitation, acceleration due to the gravity, and that's it. This will become dx. Okay, I think I just multiplied all of the constants. And you can multiply 1,000, this constant, this one, and this one. It will be 1,570 pi, and then we can just integrate this. We can see this. As we remember, let's remember all of these couple of first steps, okay? And then know how to find the volume. Volume will be different because the shape is different in each question. Okay, and I did the work. Is 3.4 times 10 to the power of 6 joules. Joules are Newton meters. Okay, one more. Okay, you may definitely pause the video at the beginning of the question and try to get the answer. You will get it. Okay, that's my solution. You can check, and this is the solution. I think it's fine. Okay. The last question has two parts, and let's solve it. Consider the trough with the shape below. We have this beautiful shape. It is full of water, which has a density of 1,000 kilograms per cubic meters. That's the density of the water. And recall the acceleration due to the gravity, of course, is 9.8 meters per second squared. Part A, write but do not evaluate a definite integral that calculates the work required to pump all of the water over the top of the tank. Okay, and that's me. Let's see what we have. We definitely need, let's say, one layer. Yes, one layer of water, because this will be helpful to figure out the volume. Oh, let me add, where am I? We have to do this. Yeah, this will be like a, okay. Am I right? The thickness is delta x. That means that's one layer of water. Let's say this is B, that base, B sub I. And, okay. That's mean what I name this distance that we have to move. This will be x sub I, because I have to take that one slab of water, if we can even imagine this slab of water. Okay. I have to think like layer by layer, that I'm removing like a layer of water. X unit up, because I can go up to the top. And then each like level of water will be moved out, but we're focusing on one. That's the reason that x sub I is the top, from the layer, from the water to the top. Okay, force times the distance. We know the distance. Now, force is mass times the acceleration due to the gravity. We know that. Mass is the density times the volume, because we have to know the mass, the density of water times the volume. And now, the question is, what is the volume of this slab? Yeah, it will be length times width times height. Actually, length is 8. That means it will be B. Yeah, the volume is B sub I times 8 and times the thickness. Yeah, it's length times width. I'm messing, times height. Perfect. Now, what is that base? Yeah, with respect to x. We need that base. What we will use? We will use the similar triangles because we have 2 and we have the height 5 and we have B, and I think that height, okay, it will be 5 minus x sub I. Okay, let's get the proportion. 2 over 5 is the same like B over 5 minus x sub I. Okay, that means B sub I is basically 2 times 5 minus x over 5. When we multiply 2/5, we can multiply by 2/5 times 5 is 2, and 2/5 x sub I. Okay, this is the base. Now let's see, base times 8, yeah? This is like width times length times height. The volume, yes, that means always the volume is different. You may notice the first line, the second line, the third line is the same for all of these questions that we do, but the volume is different. Yeah? And we also have to know the distance correctly, the distance that we're lifting the amount of water in this case, or concrete up. Okay, so now I did put, yeah, that's the density of water, that's 8 constant. B sub I is this, I think I typed correctly, delta x, gravity, acceleration with gravity, and the distance. And let's put all of the constant that we know. What I also did, I factor out 2. We can see 2 and 2. It will be just easier. And then I multiply each of them, density times 8 and times 7.8, and I keep that 2. Delta x, and I also distribute x, x sub I. You may notice x squared. And now we have to integrate this. Constant, and that's it. From 0 to 5, because we have to pump out the water from the bottom to the top, from 0 to like 5 meters high, the shape of the throw. Okay, that's part A. Now, part B, we have to do the same, right? But do not evaluate a definite integral that calculates the work required to pump all water out of spout 3 meters above the top of the tank. That's what will be the difference. It will be exactly the same, but that distance, yeah, this is the distance, force times the distance will be different. Because we will have this, like I don't know how to, and the water, and this is extra, we have to, the water must go through extra 3 meters. That means instead of x sub I, it will be x sub I plus 3. That's it. I think I have it. Let's see. Let's say part A, and let's say part B. Actually, let me remove this because this belongs to the part B. It means now we will have a distance. The water will go 3 meters. This is the amount of water, right? Oh, how beautiful I'm drawing now for the second time. Okay, that means this. Oh, I'm pressing, but yeah, I can show you. This one is x sub I. That's we have to move that amount of water, each of them, because integration is taking care of every single layer of water, slab of water. Yeah, not, yeah, this will be, general. I have to add 3 and everything else is the same. I have the solution, but you may do it on your own. Mass times the acceleration due to the gravity. Mass means volume times density, density times volume. Density will be given because it's water, and we remember volume of that slab, length times width times height. Yeah, and that's the same thing, the same. It's exactly the same, but not x plus 3 from 0 to 5. That's in, please make sure that we know, yes, we know the formula. This will be the general formula, actually. Actually, this is not correct, right? Let's say distance. Force times the distance, then will be more general. And the distance in this time is x plus 3, because we have to move the water up 3 meters. It will be definitely more work, because we have to lift it higher. The water has to go higher. But please remember, force times the distance. Force is the mass times the gravity. Mass is density times the volume. Then everything else you can substitute. Looks complicated, but it is not when you simplify. Okay, enjoy computing the work. Thank you.